Okay, welcome to video 4.7. This is the discussion of the last sort of flavor of aqueous chemical reactions in chapter 4. And these have to do with oxidation and reduction type reactions or redox. And um, uh, redox reactions, in my opinion, are probably the most important of any reaction that exists, and that's mostly because, in part, I'm biased because I'm trained as an electrochemist, so it is my field of study. But it's really all of energy science. All energy science hinges on redox reactions, and it can be a tricky concept to get, but I really encourage you to dig in here because this forms the basis for really all future energy decisions you're going to make. So that's like all battery technology. Every single battery you've ever used or will ever be invented is based on a redox reaction. So all of the sort of new EV or electric vehicles, thinking about like, is it really more efficient? And the answer is sometimes, not always. Happy to talk about that. All solar cells, photovoltaics, this is what my PhD is in. Energy transfer from sunlight into electrical energy. That's redox reactions. The hydrogen fuel economy that we're aspiring towards as a society is going to require non-combustion based fuel and engine systems, which we call fuel cells. This is pure redox reactions or electrochemistry. Solar electrolyzers, so taking sunlight and converting that into liquid fuels, which then can be used in an electrolyzer or a fuel cell to make electric energy, but also all traditional energy forms, so combustion, so the way that your vehicle runs right now by burning fossil fuels or just simply lighting a bonfire. These are all redox reactions. Almost all biochemical pathways in the body, how we utilize sugar as an energy source and then breathe out to exhale carbon dioxide. That whole process, that chain from sugar all the way down this giant cascade in your body to ultimately CO2, that's electrons being shuttled in and out and in and out, and each time that happens we harvest energy. That's all of human physiology and biochemistry. So I really want to emphasize redox reactions is super important. We're going to talk a little bit about them in Chem 107, and then you're going to talk quite a bit more about them in the last week of a Chem 108 class. So it's really good to start and learn about them here. So let's do sort of a couple examples with redox reactions. I should state explicitly, so oxidation reduction reactions, what makes them different from acid-base or precipitation reactions is that an electron is transferred, at least one, from one chemical species to another. That's what oxidation and reduction really means here. So I got a few examples set up here. We're going to walk through sort of generically, and then we're going to dig into actually analyzing what these reactions are. And so oxidation, reduction, or redox reactions really, as I mentioned before, pertain to the transfer of electrons. And so we can look at the transfer of electrons in chemical species by identifying what their oxidation states are, which we've alluded to already a little bit in previous videos. An oxidation state here is really the charge on those particular ions, or the partial charge on not necessarily ions, but on atoms or molecules. So here we've got copper in this first example. Copper is in a 2+ state, meaning it's lost 2 electrons from its neutral copper 0 or copper element that you'd find in the periodic table. So on the left side of the reaction, and the reactant side, it's copper 2+, but if you look over here, it's copper 0. This is a 0 if you can't tell. And so that means we're going from an oxidation state of 2+ to 0, which means that this copper 2+, this copper ion, must be gaining 2 electrons from this side to this side. Okay, so this is crucial. So if this is gaining 2 electrons, it always has to be true in any electrochemical or redox reaction that those electrons have to come from another chemical species in solution. Electrons can't just come from thin air. So if you've identified that this species is gaining 2 electrons, then some other species in solution on the reactant side must be losing them. And in this case, all we have is zinc 0 here. So if we look at zinc 0 and then we look on the right side, it turns into zinc 2 plus. That makes a lot of sense in that the electrons are coming from the zinc 2 plus. So we say minus 2 electrons. That makes sense. So these two species here, copper 2 plus and zinc 0, are really just exchanging electrons with each other. So 2 electrons are coming from the zinc, being dumped into copper. That's making zinc 2 plus, the ion, and copper 0. Okay, so in terms of redox reactions, which one of these is an oxidation and which one is a reduction? So everybody's got a different mnemonic. The one I often use in this class is oil rig. Oil rig is a mnemonic device to help us identify what is an oxidation reaction and what is not. So oil rig stands for oil stands for oxidation is loss of electrons, and rig stands for reduction is gain of electrons. And so it's just a simple way to remember for these two reactions. So if reduction is gain, a copper 2 plus is gaining 2 electrons here. So that means copper 2 plus is being reduced. At the same time, if oxidation is loss, then zinc 0 is undergoing an oxidation reaction. Okay, so in any redox reaction, there will always be an equal and opposite reduction and oxidation. You can't just have an oxidation or just a reduction. There will always be both, meaning electrons have to come from somewhere. So something has to lose electrons for another thing to gain. So pause the video and try to work through these two things. Draw arrows like I did and identify what's being oxidized, what's being reduced. Okay, so maybe you had a chance to look at these. I just drew out generally. We don't have all the tools yet to fully identify, so I don't feel like you need to yet, but maybe your intuition is pointing you towards what might be oxidized and reduced. So in the second example, this is the oxidation or the burning of magnesium. If you've ever seen like the bright white fireworks that you'd see in like a 4th of July celebration, that's this reaction. So this is magnesium burning in air. Makes this really bright hot flame and then produces magnesium oxide. So we're starting with magnesium 0, meaning this is elemental magnesium, and it gets converted into magnesium 2 plus. We know this is magnesium 2 plus here because it's bound to oxygen. Oxygen is in group 6A in the periodic table. We know that those species in group 6A tend to be -2 charge, which means that magnesium is +2. We also could have said that magnesium is an alkaline earth metal. It's in group 2A, which means that it has a +2 charge. Okay, so we're going from a 0 to a +2, meaning we're losing electrons, which is why magnesium in this case is being oxidized. And that must mean then that the oxygen is being reduced. What we haven't learned yet, what we're going to learn in a second, is that any element that's in its pure form, its pure elemental form, like oxygen gas, we're going to say that it has an oxidation state of 0 to start with. And so we're going from an oxidation state of 0 in oxygen to oxygen being bound as an oxide, magnesium oxide here, as 2-. So we're going from 0 to 2-. So the 2 electrons that we ripped out of magnesium metal get tacked on to oxygen gas to make the oxide. So electrons are being exchanged in this system. Similarly, if we have the pure elemental form of phosphorus here, P, that again, if you have pure elemental form, oxidation state is 0. Bromine also is the pure elemental form. This is how you'd find the natural form of bromine on Earth. That has an oxidation state of 0. So any elemental form is going to be oxidation state of 0. So we're going from 0 and 0. Over here, though, bromine or bromide is in group 7A, which we know to have a charge of -1, which means that the phosphorus here, if we've got 3 of these, phosphorus must be a +3. And so in that case, phosphorus is going from 0 to +3, meaning it's tearing off 3 electrons from the phosphorus. It gets oxidized, and sort of the equal and opposite there is then the bromine must be getting reduced, which makes sense because it's going from 0 to -1, and there's 3 of them that all get reduced, which it takes account for really the 3 electrons. If 3 electrons get pulled out of the phosphorus, then 3 electrons get pushed into the bromine. We're going to walk through a bunch of these. These are just to sort of just set the stage right now. So the oxidation state of, or the oxidation number of a particular element is what we're going to use to guide us in determining whether a species is undergoing a redox reaction first, and if it is, whether it's being reduced or oxidized, just as we've done in the previous few examples. And so we were using basic intuition there and a little bit of our knowledge of the periodic table, but now we're going to sort of systematize that with a set of rules. And so the oxidation state really indicates whether or not an atom is electron rich, or poor, or neutral. So electron rich, poor, or neutral. That's what the oxidation state is. The oxidation state can be the actual charge of an ion, but it doesn't have to be. It really can just also indicate whether or not there's a bunch of electrons on that element or on that atom or not. And so it can be both. And so the first sort of rule, which I had already alluded to, was that elemental state of any atom, the oxidation state is going to be 0. And so I've got some examples here, right? If I look at the periodic table over here, everything in the periodic table is written in its sort of basic elemental form, in its neutral form. So if we look at like sodium, say, or really anything in this group 1A category, those are all going to be neutral. Where it gets a little bit confusing is why is H2 considered the elemental state? Well, the reason for that is H as hydrogen atom doesn't exist naturally. It is an element, but it's so reactive that it doesn't actually exist on its own like that. It actually exists bound to itself or bound to other things. And so the actual natural form, the way that you would find hydrogen in the environment, would be at H2. And so we call that the elemental state and say it has an oxidation state of 0. The same is true for all of the group 7 or halogen atoms that we have in the periodic table. None of these exist as atoms. They do not exist like this. They actually only exist as what we call diatomics, meaning very much like hydrogen, they only exist when they're bound to themselves or to other things. And so bromine is actually Br2, chlorine, as you'd find, say, as a disinfectant or in a pool, is actually Cl2. Those are all the natural forms which would have an oxidation state of 0 in this case. Anything else on the periodic table would just be its elemental form, not bound to anything or itself. And so all of these are examples of elemental states and oxidation states of 0. Monoatomic ions have oxidation states of 0. That's our second note here. So monoatomic ions, key word here. The oxidation state is equal to their charge. And so this is just saying that if you have an ion, whatever its charge is, as long as it's a monoatomic ion, meaning it's by itself, just one atomic, the oxidation state is exactly the same as its charge. This is where it gets a little confusing, right? Because oxidation number it doesn't, as I mentioned before, it doesn't have to be the charge, because we can assign oxidation states to non-charged things. But in the case of when you are dealing with ions, which we often are in redox reactions, then it's pretty easy. Then the oxidation state is its charge. It's the exact same thing. So if you've got sodium ion, which is different than sodium atom, right? Sodium atom is the thing on the periodic table. Once it dumps an electron, then it becomes sodium plus, and its oxidation state is now +1. The same is true for calcium 2+, aluminum 3+, chloride ion, oxide or O2- ion. So anything in its ion form. Remember, from what we talked about a couple chapters ago, the elements in this group 1A tend to, when they ionize, form a +1 ion. Anything in this group 2A form +2. here. We go over here. Noble gases tend to form 0. Halogens, or 7A, are -1. 6A is -2, -3, and so on. And so those are sort of the general rules of thumb. These are referring to their ions. So when those elements turn into ions, then their oxidation state is the same as what the charge on the overall ion is. Okay, so the third sort of general rule of thumb here is that an atom that's bound inside of a polyatomic ion, like what we're showing here, typically has the same oxidation state as it would if it were by itself as a monoatomic ion. And so this first one is actually just water. It's not really a polyatomic ion. It's just a molecule. We can break apart and just look at this molecule and then assign oxidation states to the individual atoms within the molecule. Remember, oxidation state is not necessarily the charge unless it's an ion, and water is not charged, it's a molecule, but we can still assign oxidation states. So we would assign oxidation states based on what would the atom be, what would the charge be if it were just a monatomic ion. So if we looked over at oxygen, oxygen would be in this group 6A here, which we know to be -2, -1, 0, +1, +2, -3, etc. So oxygen would be -2 based on where it is on the periodic table, group 6A. Hydrogen, as we'd shown before, hydrogen ion is the proton, that's the acidic proton, that takes a +1 charge. So, and it also is in group 1A, so that's coincident as well. And so water then has an oxygen at -2, hydrogens at +1. Collectively, then, if we add up all of the oxidation states, those should equate to whatever the charge is on that ion or polyatomic ion or molecule. In this case, 1 + 1 - 2 is 0, which makes sense because water is a neutral charge. Let's jump over to hydroxide ion. Same thing is true, right? Oxygen itself has an oxidation state of -2, but it's not actually -2 charged because it's not an ion. It's bound as a covalent molecule here. The hydrogen has a +1, so if we add these up together, these end up making a -1, which is the same as what we'd expect for hydroxide ion, which is the base. We can look at ammonia, so this is NH3 over here. So N is actually going to be in group 5, it's going to be right about here. So ammonia has a the nitrogen has a -3. Each of the hydrogens, because they're group 1A, will have +1s. Add these things up, and this becomes an overall charge of 0. But the individual oxidation states of each of these atoms is represented here. So this is a key takeaway. Again, I keep hammering this home. Oxidation state is not necessarily the charge, especially when you're dealing with neutral molecules. It's really just sort of the propensity for electrons to be residing on that type of atom. And so just as we talked about before in nomenclature and naming, we can sort of break apart the periodic table into generally either cation-like, or things that want to be more positive, which would be in this general direction, or things that are more anion-like, or things that would tend to take more negative type oxidation numbers, which would be in this general direction. And that jives with how we've assigned oxidation states for these, right? So nitrogen is -3 because it's more likely to take on that negative character, and then hydrogen is +1 because it's more likely to take on that positive cation-like character. So hopefully that makes sense. Okay, so there's always going to be weird exceptions with anything in chemistry when we're making sort of broad strokes generalizations. And so typically hydrogen, because it's group 1A, is going to be +1 unless it's not. And in some cases it can be -1. And so in the instance that it is bound to a metal, typically we call hydrogen, when bound to a metal, we call it a hydride. And that name should sort of give you some idea. Hydride, the nomenclature, means it's actually a -1. So if we have something like sodium bound to hydrogen, the sodium, because it's group 1A, is still going to be +1, but in order to make this whole compound neutral, because it's a neutral compound, this has to be -1 to make this the overall compound 0. Similarly, we could have calcium hydride, which would be calcium bound to 2 of these, hydrogens. Calcium is 2 plus because it's in group 2A, meaning this has to be -1, this has to be -1 to make the overall molecule 0. So when it's bound to a metal, when hydrogen is bound to a metal, it's often -1. When it's bound to a non-metal, then it takes on its sort of typical oxidation state. So if we've got like hydrochloric acid, HCl, then we've got Cl as a -1 because it's in group 7A, and +1, so that's exactly what we typically expect. And if we have, say, hydrogen sulfide gas, which is H2S here, similar idea. Sulfide is in group 6A, so this becomes 2 minus +1 +1 to make this overall a neutral charge. And so whether hydrogen is +1 or -1 just depends on what it's bound to. When hydrogen is bound to a nonmetal, making a covalent bond, because remember we treat hydrogen, if we go all the way back to lecture, or the lecture in chapter 2, we treat hydrogen typically as a nonmetal, and we have nonmetal bound to a nonmetal, we get a covalent bond, and then it behaves in sort of its normal way as a +1 oxidation state. But when we get the nonmetal bound to a metal, then it's behaving more like an ionic type bond, in which case it takes on this -1 character. Okay, so that's exception 1, dealing with hydrogen. So second exception here is that oxygen, because it's in group 6A, is typically -2, and that's what we've seen so far. But that's with the exception of when it's bound up as a peroxide. So let's look at sort of the general -2 oxidation state of oxygen, like in water. We have +1 hydrogens, and we have -2, that makes water an overall neutral charge. That's exactly what we'd typically expect. But when we have a molecule like this, this is the hydrogen peroxide, or H2O2, that you've used maybe for sanitation of wounds. If we look at this, now hydrogen, again, if we go back up to our sort of previous example with hydrogen, hydrogen is bound to a nonmetal, which means that it's still +1. But in order to make this overall compound neutral, that means that oxygen actually has to take on this -1 charge instead of -2 to make this overall thing neutral. If we look at the oxide anion, which is 2 oxygens bound together, but it actually has an overall charge of -2, then this is a little weird because these both have to take on a -1 charge. So again, overview, oxygen is almost always going to be -2, except when you see oxygen bound to itself, and that's what constitutes a peroxide. So something like this, or something like this. In that case, it's going to be a -1 to set the overall compound to neutral. Okay, so the last exception that I want to talk about is that halogens are typically going to take on this -1 oxidation state because it's in group 7A. So like an example would be, as we talked about before, hydrochloric acid. We've got H as +1, and then chloride is group 7A. This whole thing becomes a neutral charge, right? This is true except when a halogen, again, halogens are group 7A, when they are bound to an oxygen atom. So for example, if we have this compound, chloride or chlorine, bound to another chlorine through an oxygen atom here, in this case the oxygen atom is going to be its typical -2, because remember in the previous example oxygen is always -2 unless bound to itself. So it's not bound to itself, so it's still -2, which means that this compound is neutral, which it is, then these chlorines have to actually take a +1 charge. So it's sort of similar to the behavior of hydrogen before. It's sort of flipping between a covalent type and a ionic type bond here, depending on what it's bound to. Another example would be hydrobromous acid, which would be HOBr. In this case, we've got hydrogen in its typical +1 state because it's bound to a nonmetal. We've got oxygen not bound to itself, so it's still taking on its typical -2 charge, which means that if this overall complex or a compound is 0, then the bromine has to be taking on a positive 1. So again, halogens, anything in group A, chlorine, bromine, iodine, fluorine, they're typically going to be -1 because they're group 7A, except when they're not. And that not is when they are bound to oxygen, in which case they typically take on a positive 1 type oxidation state. Okay, so let's put this to practice here, especially with things that can take on multiple oxidation states. So sulfur, and really anything that's beyond the, or within the third row of the periodic table and beyond, can take on multiple oxidation states, so that gets a little tricky. And so sulfur is in the third row of the periodic table, so we don't necessarily know what this is intrinsically. And so let's sort of reverse engineer this compound. This is sulfuric acid, by sort of assigning what we know to start with. And so we know hydrogen, when it's bound to a nonmetal, is going to be a +1 state. So we're going to say each one of those is +1. And we know that oxygen, unless it's bound to itself, is going to be in a -2 state. And actually, you may not know this, but these oxygens are all bound to the sulfur here. They're not bound through each other. So each one of these is going to be in the -2 state. And so I'll write out what the actual charge is here. So if we have 2 hydrogens, each at +1, then we've got +2 charge coming just from here. And then from the oxygen side, we've got 4 -2s, which means that this is going to be a -8 coming from just those oxygens. And so this whole compound has to be neutral, right? It has to have a charge of 0, which right now we've got a charge of -6. That would be -8 + 2, which would mean that the sulfur actually has to have an oxidation state of +6. So we'd write this out as sulfur 6+ if you were being asked what is the oxidation state of sulfur. So similarly, let's look at this perchlorate ion here. So its charge, it's got a minus here. We've got oxygens. Oxygens in this case, this molecule looks something like this. So they're not bound to each other. They're just bound to the chlorine. And so we can say that those are all -2, but we have 4 of them. So really it's -8 coming from this side of things. The overall charge is -1, which means that the chlorine itself is going to have this wacky oxidation state of +7. So chlorine is going to be 7+ here. And so you can sort of see, based on the rules and the exceptions, we identify what we know, and then we reverse engineer what we don't know. Let's look at NH4 here. So NH4, H is bound to a nonmetal, so it's +1 like it normally is. In this case, the overall charge is going to be +1, which means we've got 4+ of these hydrogens total on this side, which means that the nitrogen must be a -3. And so nitrogen 3-, which is actually normally how nitrogen takes. So there's several of these examples on the workshop and in the suggested problems, and you just get used to these with practice. And so knowing what the oxidation state of different atoms are inside of a molecule is really the key first step in being able to identify redox reactions, and then specifically identifying what is being reduced and what is being oxidized. So this is a good thing to start practicing with now. Okay, so let's come back to this reaction that we've talked about quite a bit so far in this course, which is the rusting of iron. So this is the reaction of iron metal in the presence of oxygen to produce this Fe2O3. So this is absolutely a redox reaction. So let's use what we know and what we've learned about oxidation states and assigning them to identify what's being oxidized and what's being reduced. So let's start with iron. So remember, any elemental version of a compound or an atom is going to be an oxidation state of 0. I really prefer to just write explicitly the oxidation state of 0. Even some people don't do that. It just makes it really clear to me. So I'm going to write it right up at the top here as 0. The same is true for oxygen, right? Oxygen is one of those elements that is in its pure form when it's bound to itself. And so oxygen has an oxidation state of 0 in this case as well. So then let's jump over here. So iron here, and we've got 2 of those, and we've got 3 of these oxygens or oxides. Oxygen is going to be a -2 here, which is going to make this overall compound -6, or from this side of the contribution. And if that's -6, we've got 2 of those, then this has to be +6, which means that iron is actually going to be in its 3+ state, and oxygen is going to be in its 2- state. Make sure you pause the video and really work that out if that's unclear as to how I just deduced those oxidation states. Okay, so we're going from an iron of 0 to an iron of 3+. So I'm going to connect these this way. If I'm going from 0 to 3+, remember our mnemonic was oil rig. Oxidation is loss, reduction is gain of electrons. So in this case, we're going from 0 to 3+, which means we've lost these 3 negatively charged electrons. So that means that the iron is being oxidized, which is what rusting is. That's why some people talk about oxidation of metal. Right, that's essentially a rust. Rusting can occur with any metal. Rust is a generic type of reaction where the metal is being oxidized in the presence of oxygen. Okay, so we always know, you'll never forget this, that if there is an oxidation reaction, then those electrons have to be going or coming from somewhere, which means there's an equal and opposite reduction reaction. In this case, we've only got oxygen, so we know that that must be the thing that gets reduced here. In that case, those 3 electrons are going to be, well, and actually in this case, the oxygen is gaining 2 electrons to go from 0 to 2-, but there's 3 of them that this is occurring through, which means that this has a total of 6 electrons that are being moved, and 2 times that, which means we've actually got 2 times 3 plus 2 electrons, which is 12 electrons are actually being transferred onto the oxygen. The same number of electrons have to be moving from the oxidation side, which makes sense because we have the 4 irons. So 4 times this equals 12. So that means 12 electrons are flowing out of the iron, and all 12 electrons are flowing into the oxygen, equal and opposite. And so this is a good example of a really basic redox reaction. So there's some other terminology that electrochemists or chemists use, not just what is being oxidized, but what is doing the oxidation or what is doing the reduction. So we have these terms, reducing agent and oxidizing or oxidation agent. And so these are sort of the flip. Whatever is the reducing agent is the thing being oxidized. And hopefully that makes some sense. You can pause the video and sort of replay that. If something is doing the reducing, it must be the thing that gets oxidized, right? So let's think about this in this case. So we have iron here. It's being oxidized, which means it's giving up these electrons, all 12 of these electrons, which means it's forcing those electrons onto this oxygen, and it's reducing that oxygen. So iron is acting as the agent of reduction. So in this case, iron 0 is the reducing agent. Sort of by analogy then, the oxidation agent is the thing that is being reduced. And so in this case, oxygen, which is really where the name oxidation comes from, because it's typically the oxidation agent. Oxygen's a great oxidation agent. Oxygen gets reduced, so in this case, oxygen is our oxidation agent.